All right, so let's do some momentum practicing today. So we have a steel ball of mass m fastened to a light cord of length L, released from rest from the horizontal. At the bottom of the path, the ball strikes a hard block, mass 4m. Initially at rest on a frictionless surface, the collision is elastic. Remember what elastic means? Elastic means the initial kinetic energy is going to equal the final kinetic energy. Ta-da! How wonderful. So energy is conserved. But that's not going to matter right now, because for the first part, we need to find the tension in the cord when the ball's height is half of L. Write your answer in terms of m and g. Okay, so let's say it's right about there. We'll say that that's halfway. All right, it's still going to be connected with the string. The string is still L, so we're going to have a 30 degrees right there, because that's our special right triangle. Let's draw the forces that are acting on there. We've got gravity, and we've got tension. Tension is pulling it that way. Now, gravity and tension are at weird angles, so we're going to have to split them apart into components. Instead of splitting the tension apart into the components, I'm going to split gravity apart. So gravity has two pieces. It's got this way and it's got this way. All right, so there's two forces that we're going to worry about right now. We know this force and this force. These guys together is going to make your centripetal motion because it's traveling in a circle. So your centripetal motion is mv squared over r. That's for traveling in a circle. That's the force towards the center of the circle. And I know the force towards the center of the circle has to equal force of tension minus this force of weight here. All right. Now, since this guy is mg, and then we have a 30 here, a 30 there, you can split it apart and see a 30 there. This would be a 60 if you want to do it that way. There's tons of ways here. So we're going to have a root 3 over 2 mg, right? Because here's your right triangle. Oh, sorry, it's not root 3 over 2. It's just going to be a 1/2. It's going to be a 1/2 mg. All right, because here's your 30, 60, 90 triangle. Here's your mg. Here's your 1/2 of mg side. All righty. So we're looking for this force of tension here. We got to figure out the velocity, though. We can do that because we know that mgh is going to equal 1/2 mv squared. Cancel out the m's just like before. Now, h is how far it dropped. It dropped half of L. So we're going to have g times 1/2 of L. Kick the 1/2 over here, so it's going to be times 2, and that's going to equal our v squared. Cross out the 2 and the 1/2. So now we get GL. We can plug GL into there because that equals v squared. So we are going to have our mgl over L is equal to force of tension minus 1/2 mg. Okay, so the L's cancel out there, so we're going to have mg plus 1/2 of mg. So your force of tension is going to equal 3/2 mg. Ta-da! And that's that. All right. So find the speed of the block immediately after the collision. Okay, so they're gonna bump right there, and we're gonna find the speed of the block. All right, now it is elastic. That means there's two things that are conserved, two things we're gonna have to deal with. The first is momentum. So we're gonna have m times v. Let's just call it m times v. Initially, this guy has 0 momentum to start, so we don't have to worry about that. That's going to equal the final momentum. Now, this guy is going to have positive momentum. He's got a mass of 4m, so 4m times his momentum, we'll call it vb, or his velocity, sorry. And then we're going to subtract the ball going back the other way. So the ball is going to have M, we'll call it V, VR, V return, right? So this is VR, and this is VB for block. Anyways, so we have that for momentum. Now we also have kinetic energy that lines up. The ball has kinetic energy start. It's going to have 1/2 mv squared. V is the ball coming down here. We could figure that out, but let's not worry about that yet. It'd be the same thing we did earlier. And that's going to equal the kinetic energy of the block. So it's going to have 1/2 times 4m. So let's make it a little easier on ourselves. So 2m v block squared plus, because these are scalar quantities, they don't have a direction, 1/2 m vr squared. All right, so we've got two equations here, and we want to find the speed of the block after the collision. So we're solving for VB. Now, we're going to have to do some substitution here. So we're going to take this top equation. We're going to solve it for VR. We're going to solve it for VR and then plug it into the second one and solve for VB. If you want to get a head start, see if you can. All right, let's see. So solving this for VR. So let's do it piece by piece. We're going to have mVR is equal to 4mVB minus mv. So far, so good. All right, so V2 is going to equal, let's just cross out all these m's. That's the ticket. 4VB. Oh, sorry, V2 is VR. My bad. Looks like an R. VB minus V. All right, now we know what VR is equal to. We're going to plug it into right there, the return. Okay, so let's plug some stuff in here. Let's simplify it at the same time. Let's cross out all those m's. I'm also going to multiply everything by 2 to get rid of those fractions here. So I'm going to get v squared is equal to 4 VB squared plus 1/2 is gone. And now I'm just going to stick this in here. So it's going to be 4 VB minus V squared. All right, so far so good, I hope. Now we've got to factor it out, or FOIL it out. So V squared is equal to 4VB squared plus 16VB squared minus 8VBV plus V squared. All right, the V squareds cancel out on both sides, and let's simplify. Let's combine like terms here. So 0 is equal to 20 VB squared minus 8 VBV. All right, I know we're running short here, but we can factor this. So 0 is equal to, I'm going to factor out a 4 at the same time. So 4 VB, and then leftoverville, we've got 5 VB minus 2V. All right, this gives us two solutions. First solution is the easy one, VB is equal to 0. The second solution is VB is equal to, move that over, divide by 5, 2/5 V. All right, now this top one is not the one we care about. This is before collision, which should make sense because it wasn't moving before. And this part is the after collision. All right, we care about the after. So find the speed of the block immediately after collision. It is going to be 2/5 of what the ball was traveling on the way down. But I know what you're saying. Well, what was the ball traveling on the way down? Well, funny you should ask, because the ball was traveling at mgh is equal to 1/2 mv squared. Cancel out those m's. G times h, it dropped by L, is equal to, well, let's kick that over there, v, and then we'll square root. So this is how fast the ball was moving. What we're going to do is we are going to plug that in for here. So that means the velocity of the block right after it collided was going to equal 2/5 times the square root of 2 times g times L. All right, whatever those measurements are. Nice. And that's it for part B. Not too bad, right? Hopefully you remember doing this. For part C, to what height will the ball rebound after the collision? Well, this sounds like you'll have to do the whole thing over again. And you're right, but you don't really have to do the whole thing over again, because we have this equation right here. We know what the velocity of the ball was. So what we can do is just plug it in to figure out what the rebounding velocity was. Or this is the block, sorry. So we need to just figure out what VR is. And we know what V is because we just figured that out right there. So VR is going to equal 4 times VB. VB was 2/5 the square root of 2GL. All right. Minus V, which was the square root of 2GL. So far, so good. 4 times there is going to be 8/5. 8/5 minus 1 is going to be 3/5. So VR is equal to 3/5 times 2GL under the square root. Okay, and that should make sense if the ball took away a bunch of the velocity. Well, the block took away some energy. The ball is going to get the rest of it now. Okay. So what we are going to get is we're going to use this in our conservation of energy again. So what we're going to have is mgh is equal to 1/2 mv squared. Cancel out those m's. This time we know the velocity. The velocity is this guy. And we're going to figure out what the h is. All right. So plugging that in, we're going to have gh is going to equal 1/2 times, parentheses, 3/5 square root of 2GL parentheses square root. All right, let's distribute that and simplify it a little bit. So GH is going to equal 1/2 times 9/25 times 2GL. The 2 and the 1/2 can take each other out. The G's can cancel out. So what you're going to have is H is going to equal 9/25 of L. And that's it. All right, wasn't that fun? Let's do another problem. All right, for the second question, a ballistic pendulum is a device that may be used to measure the muzzle speed of a bullet. Composed of a wooden block suspended from a horizontal support attached to each end. The bullet is shot into the block. The result is a perfectly inelastic, there's important, impact. The block swings upward. Consider the bullet mass m with a velocity v as it approaches the block mass big M. The length of the cords is L. The maximum height to which it swings upwards is y. And then we have an x for a displacement horizontally. Nice. All right, lots of letters here. Gives you a wonderful picture with all this jazz on it. Okay, so for the first one, find the speed of the bullet. So we are going to start with the speed of the block, because that is easier, and we can use momentum, because momentum is awesome. So the speed of the block after the impact is going to equal mgh is equal to 1/2 mv squared. These m's are for the block, so it just cancels out anyway, so who cares? So v of the block, we'll say of the, we'll say P for pendulum because B is for bullet, how about, is going to equal the square root of 2GH. Now, of course, the pendulum is really going up by Y, so we'll throw in the Y for there, 2GY. So this is for the pendulum, but of course, that's not all. We actually want the speed of the bullet, so we got to use momentum here. The bullet starts out at mv, and then it's going to be moving inside of the pendulum. So the pendulum starts off at 0, so no momentum there. So the pendulum's momentum is going to equal the pendulum mass, which is m plus the little m, because the bullet's stuck inside of there, times the velocity of the pendulum, which we just figured out right there. So multiply by 2GY under the square root. So that means the velocity of the bullet is going to equal m plus little m, let's divide by little m, times 2GY square root. Nice. So that is the velocity of the bullet. All right, moving on to part B. What fraction is lost as a result of the collision? What happens to the total kinetic energy? All right, so what we're going to do, let's figure out the amount of kinetic energy that it kept first, because that's going to be a little bit easier, and then we'll just subtract them there. So what fraction was kept? Well, that's going to be the kinetic energy of the pendulum divided by the kinetic energy of the bullet, because the bullet had a bunch, and then it lost some going into the pendulum. So both the formulas are going to be, let's do the denominator first. That's easy. So for the bullet's going to have 1/2 mv squared. Ta-da. Now the numerator here, the pendulum, is going to be 1/2 times the mass of the pendulum, which is going to be m plus little m over little m. That guy again, oops, sorry, no denominator there, times the velocity. The velocity is going to be this guy right there, the one that we figured out. So this is going to be a square root of 2GY. Ta-da. And that's that. So doing a little simplifying here, because yes, we can cross out those 1/2. Now I'm going to rewrite this as a two fractions, sort of, as in like the part that's squared and the part that's not. So the part that's not squared is going to turn into m plus little m divided by little m. It's just the left-hand side of that stuff there. Now for the stuff that is squared, this guy is going to be a 2GY in the numerator. Now this v here, we have something for it. It's this guy right there. So what we're going to do is we're going to stick that whole thing into here. So this is going to be big M plus little m divided by little m. Now I'm going to distribute the square at the same time here. That's going to be squared. And then this guy is going to be 2GY. And now you see these guys take each other out. So where we're at is we're right here. Now we've got this guy. These are the same thing as each other here. So this one, we've got one in the denominator that's squared and one in the numerator that's not. So what that means is you're going to have 1 over m plus little m over little m, which is the same thing as little m divided by big M plus little m. All right, and that should make sense because this is the keep fraction, which should be less than 1, and in fact it is. So the KE lost fraction is going to be 1 minus m over big M minus little m. That's a little m. It's going to be 1 minus that. It's going to be the rest of it. And that's that. Okay, looking at part C. If y is very small, so y squared can be neglected. Hint, hint, so we're looking to make a y squared that we can get rid of. Determine the speed of the bullet in terms of stuff with x and L. All right, so this problem isn't really so much a physics problem. This problem is a geometry problem. Let's look at this triangle right there. Isn't it a lovely triangle? You're saying, Mr. Keeney, it's okay. And I'll say, you're right, it's all right. Because it's a right triangle. And we know some of the sides of this triangle. This side is x, this side is L, and this side is not y, because y is right there. So L is also this length here, so this side is going to be L minus y. All right? So what we're going to do now is we are going to do your old friend, yes, the Pythagorean theorem. A squared plus b squared equals c squared. Let's get the tough one out of the way. So we're going to have L minus y squared plus x squared is equal to y squared. Yes. What? That's not a y. This is an L. I don't know what you were thinking when you told me that was a y. Anyway, so let's distribute this here. So we're going to have L squared minus 2ly plus y squared plus x squared is equal to L squared. Okie dokie. Now there's some fun stuff we can do here. For example, we can cancel out the L squareds. And then what else? Oh no, I don't remember. Y squared can be neglected. Oh, poor y squared. We barely got to know you. Anyway, so once we have that, now what we can do is rewrite this as an x squared minus 2ly is equal to 0. Now, it doesn't say y can be neglected, so just y squared. So let's solve for y here. So x squared is equal to 2ly. So far, so good. And then y is equal to x squared over 2l. So we want to know the speed of the bullet. The speed of the bullet is this guy here. Well, now we can just plug in some stuff for y. So v of the bullet is going to equal big M plus little m over little m. You just can't get away from that fraction. Times the square root of 2g x squared over 2l. All right, and yeah, we can get rid of those 2's. I suppose it'd be the courteous thing to do. So VB is equal to big M plus little m over little m is equal to times square root of x squared over g. Hold on there. There's all sorts of stuff not good with that. G is in the top, and L is in the bottom. Okay, now we're all set. For part D, last one. Oops. New color here. Once the block begins to swing, does the momentum of the block remain constant? No, of course not. Why doesn't the block remain constant? Because it's changing direction. Remember, momentum is a vector, so when it starts off, it's going this way. Further on, it's going that way. That is a delta P. There is a change in momentum, of course. Oh, I don't think we answered this one. What happens to the lost kinetic energy? Well, it's going to break bonds. It's going to do all sorts of stuff. So there's heat, right? The bullet will be hot. The friction will be hot when it runs into the wood. It'll break the bonds of the wood. It'll split apart the splinters or the atoms, right? It'll separate those covalent bonds. Anyways, so that's what happens to lost energy. This is why there's no way that momentum is constant. Okay, hopefully you had fun. We'll see you on the next one.